Good morning, AOBI. This is Mr. Dunning. Stand by. I have a math lesson for you. Yesterday, we spoke at the close of the lesson about today's lesson. Today's lesson involves area. Area is very useful to us if we want to find out how many yards of carpet we'll need to put in a room, how many gallons of paint we'll need to cover a wall, how many shingles it will take to roof a house. So area comes into play in many, many ways. We're going to begin today's talk with quadrilaterals. Today's talk specifically is going to discuss squares, rectangles, and parallelograms. Let's take a look at each one. In a square, all the sides are equal, and if we call the length of a side S, or side, then the area of the square is going to be S times S, or S squared. Our next stop is rectangles. This goes back to your days in elementary school when you used little tiles called manipulatives, and you would arrange the tiles in a pattern like this, and you would be asked how many tiles were in the picture. Well, you have 2 rows of 4 or 4 columns of 2, and you would correctly answer there's 8 tiles in the picture. So more generally, we have the length times the width. 2 times 4 is 8. In a parallelogram, we have a slightly different problem. There's angles here, and we can't fit square tiles into the shape unless we do something sneaky. If you can see in your mind that if we move this piece over here, we have a rectangle. And so once again, the formula that we had for rectangles will work, except that we change the names. And these names are going to apply from here on out. The long piece we call a base. This piece we call a height. And so the formula stays the same because in this, our height would be 2, and our base would be 4. In the picture of a square, the base and the height are the same. So generally, when we look at a quadrilateral, we have this formula. The area is the base times the height. Mathematically, we write that the area is the base times the height. That's going to be a jumping off point for the area of triangles. But before we jump off, let's look at a problem where you have to use this formula. In this problem, we don't have a full rectangle. There's a piece missing. Now we can accommodate that piece in one of 2 ways. Way number 1, usually the easiest, is to figure the rectangle as though it was complete. And then from it, subtract that piece. Let's do that now. Our basic rectangle is 10 by 20. But from our basic rectangle of 10 by 20, we need to subtract this little piece. So put on your thinking cap. If this is 8 and this is 10, then this little piece here is 2. If this is 20 and this is 16, this little piece is 4. And so we have a rectangle 2 by 4. To do this calculation, we multiply the 10 times the 20, and from it subtract the 2 times 4. 200 minus 8, 192. Another way to do the same problem is to break this into two rectangles and add them together. This rectangle is going to be, oh, we need to do a little arithmetic here. This piece is 16, this piece is 10, so the area is 16 times 10. In this rectangle, we have 4, the difference between 20 and 16, and 8. 4 times 8 is 32. Doing it this way, we add these two areas, 16 by 10 and 4 by 8. 160 plus 32, 192. The total is the same. Two different ways to attack the same problem. Our next stop is to figure the area of a triangle. To help us think clearly, we're going to begin with a rectangle. It has a base and a height. Then we're going to use a diagonal to cut that rectangle in half. Common sense would tell you that each of these two triangles is half the area of the rectangle. The area of a triangle is given to us by 1/2 the base times the height. If the triangle is a right triangle that has a right angle in it, the problem is easy. You'll multiply the two legs of the right angle and take half of that. In this triangle, we have a right angle, so we would multiply the 3 times the 4 and take half of that. In this example, the triangle is not a right triangle. There are no right angles here. It is an equilateral triangle. All the angles are 60, but we're going to need to do some work because we need this piece to find that red piece, the height. Well, there's a relationship here in a 30, 60, 90 triangle. Let's look at that. The 30, 60, 90 triangle is one of the most commonly used triangles for this problem. So it would be worthwhile to take good notes here. In a 30, 60, 90 right triangle, the lengths of the base and height are easy to find. Remember, we get a 30, 60, 90 triangle by cutting an equilateral triangle in half with an altitude. That gives us this 30, 60, 90 right triangle. But let's look at the relationship if we begin with all of the sides of the triangle 2, then common sense tells us that this piece is 1 and that piece is also 1. That's all we need to find the length of the height. So what we're going to do is erase that part of the picture because we don't need it. And we're going to use Pythagoras. Pythagoras tells us that the sum of the squares on the two legs, h squared plus 1 squared, is the square on the hypotenuse. When we do the arithmetic in the Pythagorean theorem, h squared plus 1 squared is 2 squared, we get h squared plus 1 is 4. H squared is 3, and h is the square root of 3. So this piece, h, will be the square root of 3. That's a Pythagorean triple. And you've got to remember it because you're going to see it in just a moment. In this problem, we have to find the area of an equilateral triangle whose sides are 8. Now that we have the same picture that we had before, let's erase the part we don't care about. And see if we can come up with what's going on here. Remember, this is the piece that would be 1, this is the piece that would be 2, and this is the piece that would be the square root of 3. But this piece isn't 1, this piece is 4, this piece isn't 2, it's 8. So we have a multiplier here. Unless you reside on some other planet, you can see the multiplier is 4. 4 times 1 gives us 4. 4 times 2 gives us 8. So this piece is going to be 4 times the square root of 3. Now we have what we need to compute the area. The area of a triangle is given by the formula 1/2 the base times the height. This piece here is 1/2 the base. This piece here is the height. And there you have it. The area of this triangle, the whole thing, including the part we erased, is 16 times radical 3. Equilateral triangles give rise to this 30, 60, 90 triangle, and the relationship one radical 3 2, and the relationship 1 radical 3 2 times some multiplier, and there will almost always be a multiplier. Next, we're going to turn our attention to circles, but we're not going to leave triangles out of the picture. I think you'll see why in just a moment. In this picture, we have a circle, but what we're going to do is we're going to break this circle into triangles. And then we're going to break the triangles into smaller triangles. So now we have 16 red triangles. I think that you can see if we keep doing this and doing this, that eventually the bases of the triangles are going to be the same as the circumference of the circle. Okay? Adding all these bases together will give us the circumference of the circle. Looking at just one of those 16 triangles, I think that you can see that the length of the height of the triangle, that piece, is going to get closer and closer and closer to a radius of the circle. In fact, when we get gazillions of these triangles in a circle, the height of each one is actually the length of a radius. So we have a formula that tells us the area of the circle is going to be the sum of the triangles, where each triangle is 1/2 the base times the height. The bases add to the circumference of the circle. The height is equal to a radius. Now let's make that substitution. When we make the substitution, the area is 1/2 the circumference of the circle times the radius of the circle. In this formula, I think you can see that the 2's will divide out, leaving pi times r, or pi r squared. So the area of a circle is given to us by the formula pi r squared. What would be the area of this circle? Well, we don't have a radius, we have a diameter. Each radius here would be 10, because a radius is half the diameter. So the area of the circle would be pi times the radius squared, or 100 pi. In this example, what we want is the shaded area. So we have to take the area of the circle and from it subtract the area of the triangle. The area of the circle is given to us by pi r squared. Radius is 11. The area of a triangle, an equilateral triangle with sides 8, if you remember, is 16 times radical 3. This gives us the area of the shaded portion in the picture. The area of the shaded portion, 121 pi minus 16 times radical 3. The answers to some of these questions get a little bit weird looking, but that is the shaded area. In this picture, we have two concentric circles. Concentric means same center. And our problem is to find the shaded area. That shaded area is called an annulus, like a ring, annulus, round. To find the area of the annulus, we need the area of the big circle minus the area of the small circle. The area of the big circle will be pi times the radius of 5 squared. The area of the small circle will be pi times 3 squared. (25 pi minus 9 pi gives us 16 pi, the area of the annulus. Working with the area of circles and rectangles and triangles, we can do all kinds of different problems. Let's look at one more before. In example 5, we want to find the shaded area. And we're given this rectangle inscribed in the circle. It has a height of 7 and a length of 24. So right off, we know the shaded area is going to be given to us by the area of the circle minus the area of the rectangle. Just from the picture, we can see the area of the rectangle now, the area of the circle. Well, once again, I have tasked you to remember your Pythagorean triples. This right triangle is a Pythagorean triple. 7, 24, 25. Well, if this piece here, this diameter is 25, then the area of the circle will be, the area of the circle will be pi times 12.5, half of 25, squared, minus the area of the rectangle, 7 times 24. 12.5 squared is 12 and a half times itself. And again, in this picture, the end result for the shaded area is an expression that looks kind of weird, but this is that area. $156.25 pi minus 168. In review, we looked at the area of quadrilaterals. We did that first so that you could remember base times height. Then we looked at the area of triangles. 1/2 the base times the height. Then we looked at special triangles, the 30, 60, 90 triangle, and used that in 2 examples. Our crowning achievement was to figure the area of a circle as pi r squared. Then we used that in 3 examples. As always, you've been a fantastic audience. I hope you have a wonderful day. We'll see you tomorrow with your quiz. So look forward to doing some of these problems tomorrow.